So today starts our first day of prep for pre-calculus for next year. And a big part at the beginning of pre-calculus is functions, their properties, and piecewise functions is one of the first topics that you will cover. So we're going to review graphing them. We're going to review all the properties. This is page 3 of your packet. So a piecewise function has pieces where the domain is split by restrictions listed on the right-hand side. So the way I like to graph them is make a table of values. And you don't have to use different colors. I'm doing that just so that you can clearly see what piece is which from the equation. So this is x is greater than 1. You have to start at 1 because that's going to be an open circle on our graph. And then we're going to substitute in a few more numbers greater than 1 to get the y values. So we'll do 1 plus 5, 2 plus 5, 3 plus 5. And then we're going to do the same thing for the second piece, and this is every x less than or equal to 1, so we'll start with 1. And because it's or equal, we do a closed dot. And then we go less than, so let's do 0 and -1. Substitute those in. -1 minus 4 is -5. 0 minus 4. And negative of -1 is positive. So 1 minus 4 is -3. So now we go plot our points. So 1, 6 is an open circle. So that's saying we're going to get really, really, really close to that location or that coordinate, but not exactly equal there. And then we got 2, 7, 3, 8, and we connect the points with array. Then we're going to do the other set. We got 1, -5. Color in the point because we're or equal at 1. And then 0, -4. And these are functions. So if you graph your pieces and they is not a function or doesn't pass the vertical line test, you know that you're wrong. All right, let's do all our properties. Domain are the x values. So we go from left to right. Since this is going to continue or equal here at 1, and then that's going to continue, the domain is all real numbers. The range, there's nothing to our graph until we get to this lowest y value, and then it continues up forever, and this gap in between is going to be handled as this piece continues. So the lowest y value is -5. So you can either say y is greater than or equal to -5, or the precal notation is going to be a square bracket. We're equal to -5, and we go to infinity. So we're going to move from the inequality notation to this interval notation when you get to precal. The y-intercept is this location. It's -4. The x-intercept, let me keep counting my slope to get exact values. So let's see, that's at 1, 2, -1, -2, -3. Another way you could solve for that if it was far away, and let me just double check when does 0 equal a -x minus 4? Yeah, I counted that wrong. So if I solve this, I get x is -4. Where did I count wrong? Oh, this isn't down far enough. 1, 2, 3, 4, 5. Oh man. This whole array is wrong. 1, 2, 3, 4, 5. There we go. So now it would work 1, 2, 3, 4. I knew that didn't look right. Okay, sorry about that mistake. So you can either solve for the x-intercept or you can count for it. This is the piece that crosses the x-axis, so I set it equal to 0 to solve for x. Oh, the zeros and the x-intercepts are the same thing. So for increasing and decreasing, we always read the graph from left to right. So this piece is decreasing. So we are that's decreasing from -infinity to 1. And then this piece is increasing from 1 to infinity. The curved bracket, or the rounded bracket, means not equal to, and the square bracket means or equal to. So now for type of discontinuity, we have to review, there are 3 types, so I'm going to add those at the top here. There is a point discontinuity, where just the point is missing. In our rationals unit, we called it a hole. The official name is a point. A jump discontinuity is when there's a jump between your pieces. And then an infinite discontinuity is actually a vertical asymptote, like from our rationals unit. So this would be an infinite discontinuity. So for this graph, we have a jump that happens at x equals 1. It's not removable. Point is the only removable type of discontinuity because you can remove it by putting in the coordinates of the hole. So it's not removable, so there's no answer for that last one. Okay, we're going to repeat all that again for numbers 2 through 5, and then numbers 6 through 8 are your homework. I'm going to make a little table. So -x minus 5. And I want that for every x less than or equal to -3. So -3, -4, -5. Then I want x plus 3 for greater than 3. So I have to do 3, 4, 5. When it's not or equal, you still have to include that number because that's where you put your open circle. Okay, substituting in -3 to this piece, we get -2. Substituting in -4, -5. Then we're going to do the same thing with x plus 3. So 3 plus 3, 4 plus 3, 5 plus 3. Okay, I'm going to count my grid better this time. The piece goes this way for every x less than -3. And then the other piece starts over here at +3. 1, 2, 3, 4, 5, 6 with an open circle. Okay, the domain. This one has an interesting domain because there's a gap between these values. There is no x that exists between -3 and 3. So we're going to say the domain goes from -infinity to -3, including that -3. And then starting at 3 but not equal to infinity for this piece. The range, there's nothing until we get to -2. And then everything else is included. So we go -2 to infinity. There is no y-intercept. There's nothing here. We can see the x-intercept, which is the same thing as a 0. And for increasing and decreasing, we are decreasing until -3. And then increasing again, or keep going from 3 to infinity. Because these pieces don't line up at an x value, it is a jump, but I can't say a point that happens at because they're not lined up like these pieces were. Okay, number 3. So we're gonna pause the video here for you to try it. Get your pieces, get your properties, and then we will unpause the video and show you the answer. Okay, so here's your answer for 3. The -2x minus 1 I graphed in orange, and the 1/2 x plus 4 I graphed in blue. So it's okay to have a decimal for a y coordinate. You can plot that and estimate it. You can count your slope, because I know this is up, rise over run. So from here I can go up 1 and over 2, up 1 and over 2, up 1 and over 2. For your properties, the domain is all reals, but x cannot equal -2. We could also write that in interval notation where it's -infinity to -2, and again from -2 to infinity. So the rounded brackets just show that you're skipping over the -2. The range starts here at 3 and goes up, but it's not equal to 3 because both of these were an open point, so that's a curved bracket. The y-intercept is 4. There are no x-intercepts here. And then we are decreasing from -infinity to -2, and then increasing. What's unique about this problem we haven't seen yet was that this has a point discontinuity. It's removable. So the discontinuity is point. It happens at x equals -2, but now that it's removable, the coordinates that will remove it are -2, 3, and you can see both of those here in your tables of values. Okay, pause the video again and try number 4. Here's your solution of 4. Because it's x squared plus 1, I know that's quadratic. I substituted in more values so that I could get the whole curve. I wanted to see both sides of the vertex, which is here. So I wanted to make sure that I got a nice picture of the quadratic piece. And then the -x is my orange one. And then unique for properties is the range. So it goes -infinity to -2 and equal, because it's a closed point here. And then again, equal at 1 to infinity. And we don't have to skip this y value because it's included on this part of the parabola. That's a funny looking infinity. Okay. On your increasing and decreasing, this part is decreasing until 0, so -infinity to 0. And then we're increasing from 0 to 2, because it's the x value of 2. And then we're decreasing again from 2 out to infinity. It's decreasing. This is a jump discontinuity at x is 2. Okay, pause one more time to try number 5. And here's your answers to 5. Again, with the quadratic, I made sure to look a little bit past the vertex in the direction of the included values. So if this was the vertex here at 0, -3, the entire beginning of pre-calculus, whether you are in honors or regular, will be no calculator. So it's important that you know the shapes of these graphs and can get your y values because the whole first semester of both courses is no calculator. So speaking of no calculator, let's find our x-intercepts. We see that it's the quadratic piece that crosses the x-axis. So where does x squared minus 3 equal 0? We're going to add 3. And when you square root both sides, it's plus or minus root 3 as a solution. However, we know that there's no negative x value for the x-intercept. It's only over here. So that's why we take the positive root 3 as our 0. But you can't forget this plus or minus when you're solving. That's a very important process concept. When you're solving a quadratic and you square root both sides, you need the plus or minus. Okay, other properties. The range, we go from negative 3 here up to infinity. This is decreasing to negative 1. Oh, that should be a negative. And then I had to skip over a little bit because we can't just say negative infinity to 0 because we have to say, okay, then we're jumping over that piece, and now negative 1 to 0 is decreasing, and then 0 to infinity is increasing. It's a jump at x equals negative 1. And now for your homework, you're going to do numbers 6 through 8, and don't forget to check your answers in Drive.